Hopefully you had a chance to read the first chapters of the two references. I think Nick sent me a link to the first book, so hopefully you could download it. Second book, if you have any issues, let me know getting access to it. Anybody had problems getting access to the books? All of you have it? Okay, good. So I just as a reminder that actually both I think Rocket's book came out in 2007, so it's been 8 to 9 years now since then. So and things move fast. So and I think if you read the chapter, he says that very clearly that it's a very fast-moving field. And and similarly, if you read Weisbuch and Winter's book, it's somewhat of a typical French fashion. They're very apologetic that there's a very lot of work being done. So how do I write the book and all that? But then they write a great book in the end. So please read if you haven't had a chance to read them. But if you have read it, maybe we can just very briefly talk about what is it that they stress a lot in the first chapter. I mean, there's one point that both books really stress on. There are things that are getting small, heterostructures, compound semiconductors, but what sort of singular thing that made these things, semiconductors as useful as they are today? What single point that they stress on a lot? Did you get such a feel that there's one point that is stressing on? Sir, yeah? Nick, yeah. Sure.
A lot about just having the control actually being structures, so having the techniques like CPD and MD.
Yeah, the techniques and the control, right? Control over purity, right? And that's really the key. Meaning, these are the most pure materials that have ever been created. And that's what they really stress on. I think. Rocket's book, he goes on into an example of saying in every 100 meters square in US, if there was a tree, then there's one tree out of the whole US would really destroy the semiconductor. That's the level of purity you're talking about. Parts per billion and all that. And what we are going to start with is today. Last class we kind of did a very rough outline of what we are going to cover, but today we're going to really start diving deep into the science, the material science, and we are starting to look at the second chapter. And as I said, I mean both the books were actually written around the time. Actually, Winter's book was Weisbuch and Winter's book a little earlier, but Rocket's book was written around the time some of these 2D crystals also were coming along. So I feel now that if you want to look at some of the fundamental electronic and photonic properties of semiconductors, the approach to first understand it may be a slightly different approach from the ones taken in the book might be useful. In the end, we are going to end up covering what's in the book, but I want to start with a slightly different approach from the book. But you please append it by reading the book, because I feel the more you read, the broader picture you get, and you append it by what I cover in the class. So we had just started. One of the motivations to look at properties was if you take a semiconductor and you shine a laser or light on it, and you start increasing the wavelength, or you start increasing the energy or decreasing the wavelength of light, what sort of absorption coefficient would you measure? Right? That's what we had started with, and this will motivate a lot of the electronic and photonic as well as thermal or vibrational properties of semiconductors and compound semiconductors in particular. So we're going to look at this problem in some detail, and actually over the whole semester. We are going to come back to this problem about the light interaction with matter. And it's kind of, very much of an analogy to if you want to know about something, you need to look at it, find out what. So you're probing it optically, and light has been really the key in probing into the properties of not just semiconductors but many materials, right? So what I want to start with, though, and remember what we're looking at here is the absorption coefficient, and if I take a chunk of semiconductor and shine light through it, so this is how much the light would, decay. So the experiment was, if I take a chunk of the semiconductor and have a light of intensity I0 on this side, what comes out here is minus alpha times the thickness d, right? And so the light has interacted with the matter that's inside this chunk, maybe a compound semiconductor or graphene or whatever, and it comes out, right? And we are really looking at a plot of this, right, the alpha. And there's a distance here, so alpha times d must be dimensionless, and so it's in inverse centimeters, right? So, and just as what we are going to first look, so I had mentioned in the last class, every little blip here tells you a lot about what's going on in the material. There are transitions of electrons. So by the way, so light is an electromagnetic wave, that much we know, right? So light is an electromagnetic wave, meaning you have electric fields and magnetic fields going, oscillating in time and space, right? So that's the meaning of light. Looks like E naught, we can write it as k dot r minus omega naught t, right? And that's the electric field of that electromagnetic wave. I think you know that you take the real part of it to find the actual electric field. So this is, right? And this is omega naught is the frequency of light. And if you multiply it by Planck's constant, you get the energy of one photon. That's the quantum theory of light. This is the classical theory of light, right? Maxwell equation gives you this. Pass over to quantum mechanics. You say that, well, light is not really continuous. I mean, the electric fields are not, energies are not continuous, but comes in packets of this much, right? H bar omega naught. And that's what's on the x-axis here. That's the x-axis here. So H bar omega naught is the energy. So these are very low energy photons, milli-electron volts, about 0.1 electron volt, 1 EV, getting close to visible. Visible is about 2 EV or so, right? 1.9 to 2 EV or so. And then you go into, 10 electron volts is ultraviolet, right? So you can't see it. So, yeah. So H bar omega is the energy of the photon, and I think the energy is related to the wavelength of photon, right? And I think we know that the energy of a photon is related to momentum of the photon by this quantity, right? That's Einstein's big result, right? Momentum of photon times speed of light, and momentum according to, again, I'm just going through a little bit of a contorted thing here. Momentum of anything according to de Broglie is h over wavelength, right? Planck's constant over wavelength. So that's really a relation. hc by lambda is equal to the energy, right? And you plug in, I don't think there is any dispute over what is h and what is c, right? You plug them in, and what you'll get here is a very useful result. So if you express the wavelength in microns, this will be the energy of the photon will be 1.24 over the lambda in microns. This will be in electron volts, meaning if your wavelength of light is 1.24 microns, the energy of that photon is 1 eV. Right? So that's the meaning. Similarly, if it is 0.1 micron or 100 nanometer, that's UV now. 100, then it's 12 eV and so on. Right? So that's, and I think this is something you probably have seen. If you haven't, this is an extremely useful thing to remember. 1.24 over the wavelength is equal to the energy of light. Okay, so I just wanted to say that part of it. And then the particles of light, classically people understood why light behaves this way. Why is it that as light goes through matter, be it a semiconductor or a metal, why is it getting absorbed? And the classical picture of light is an oscillating electric field, right? It's an oscillating electric field, and matter has electrons kind of bound to atoms, and as the electric field goes through, that electron will be basically yanked back and forth, and if the field is high enough, it will be stripped off, or something like that. I mean, that was the kind of called the Lorentz model of solids. Okay? Now that we do know quantum mechanics, you can actually say a lot more, obviously, especially a lot of the sharp transitions, the band edges, and things like that. So we're going to look at that. But classically already you can say a lot about things like dielectric constants. You can say a lot about real and imaginary part of absorption coefficients from classical theory as well, without invoking any quantum yet. Okay, so let's use this part of the result and just the picture of what is light and what are we probing, and then move over to a simpler system, because there's a lot of stuff going on here, right? There's transitions between many different states of electrons, right? And then there are vibrational modes. These are not electronic transitions, but the whole crystal starts vibrating when you excite phonons. And then you have this very sharp transition here. We're going to actually start by looking at this sharp transition first, and then gradually make our way into the smaller little wiggles here. So start the major part here. The major part for compound semiconductors, if you look at the absorption coefficient, the order of magnitude of this absorption coefficient for compound semiconductors, if the photon energy is larger than what we're going to look at is the band gap of the semiconductor. And we're going to, by the end of the class today, I hope we have a full clear picture of all these quantities, band gaps, and why this is so and all that. Okay. So this would be of the order, not exactly, but of the order of 10 to the power 5 inverse centimeter, of the order. You want to convert into nanometers, because a lot of stuff happens today in nanometer scales. So 10 to the power 5, 1 over centimeter, and 1 centimeter is 10 to the power, what, 7 nanometers, right? 10 to the power 7 nanometer is 1 centimeter. So that is about 10 to the power minus 2 per nanometer inverse. What does that mean? Let's say I want my light to be absorbed such that what comes out here is 1 over E times what came in. 1 over E. How much do I need? How much thickness do I need to absorb that light? From here, basically alpha times D. So if alpha is 0.01 nanometer, you need 100 nanometer to absorb, such that you drop the light intensity by a factor of E, right, which is 2 point whatever. Right? So you absorb quite a bit within 100 nanometer. And this is a very important property of compound semiconductors. This is a reasonably large absorption coefficient, and we are going to relate it to, over this course, to the details of the electronic structure of the compound semiconductor, the band structure, and all that stuff. We're going to relate it. It's obviously very strongly related. In fact, what we will see is a very simple result, that the absorption coefficient of a semiconductor is equal to, or rather, let me not write equal to, because I have not shown anything, is proportional to the density of states of the compound semiconductor. And it will look something like that. If you know the density of states, the absorption coefficient is equal to the density of states. With a slight change, it has a sharp edge at the band gap. So, yeah. And so the larger is the density of states, the better you can absorb the light. And you can immediately see it has huge applications in solar cells, in photovoltaics, because it tells you how much matter, how much of the semiconductor material do you need to absorb light completely. Right? In a solar cell, you want to absorb all the light in as thin a layer as possible, and therefore you need a very high absorption coefficient in a solar cell. And therefore, the best solar cells today, the ones that go on, for deep, space missions. I mean, when you get very far from the sun, there is very little light left. Or the highest efficiency solar cells are all made of compound semiconductors today. All made up because they can absorb a lot of light in a very thin distance. So this is what. Yeah. Okay. So now, as over the last 7-8 years, there's a discovery of these 2D crystals now, graphene and others, molysulfide and others, which are atomically thin, very, very thin, right? And so now the question is, how much light do they absorb? And this is a very interesting question, because you see this unit here is in inverse centimeter. So this is true for three-dimensional semiconductors, like compound semiconductor, gallium arsenide, gallium nitride, and so on. Inverse centimeter. In fact, the absorption coefficient we'll see when we talk about it for 2D crystals is actually dimensionless. It just reduces, it's dimensionless. And we'll see for graphene, it's very interesting. Graphene is not a compound semiconductor, but for it, it will be related to the fine structure constant. It's basically h bar times the fine structure constant. It's very interesting. It's about 2% absorption per layer of the semiconductor. We are going to see that. So just pointing out a few of these things in the beginning before we delve into the details. Okay, so what we'll do now is look at an even simpler problem when we have light incident not on a chunk of semiconductor, but to probe the microscopic details of this problem, we're going to look at the simplest light matter interaction, where light interacts with atoms directly, separate atoms, not a crystal. And that is obviously a historically very important problem. I think it gave birth to quantum mechanics in the first place, right? This problem gave birth to quantum mechanics, where what you have is basically you generate broadband light, all kinds of wavelengths, and you look at the spectrum of light. You have, very short wavelengths, UV, then you have blue, green, yellow, red, and infrared. It's in continuous spectrum. And then let's say you have hydrogen gas, pure hydrogen. There's nothing. It's hydrogen atoms. Somehow you have managed to make atoms. This is not molecules, but atoms. So once it becomes molecules, things change again. So it's atoms. Or how about this? Instead of hydrogen, let's look at helium. Helium it doesn't want to form molecules normally unless you make it a superfluid or something. So it's a helium gas, and you have basically you pass light through it and look at what comes out on the other side, right, after it gets through. And what you see is basically still a continuous spectrum, but some lines are missing. These are called extinction coefficients. These are very old experiments. These are ones that kind of gave birth to quantum mechanics in the first place. So some of these lines, very sharp lines, are missing. And then if you look at it with a spectrometer somewhere else, meaning the ones that is not transmitted, but what is called as emitted, those missing lines show up here. The missing lines show up there, and that's and these are very, very sharp lines. Very sharp lines. In fact, they are so sharp that you can basically fingerprint the atoms that way. In fact, today they are used. So if this cloud of gas is moving away from you or moving towards you, the sharp lines will have a little Doppler shift. It's very sensitive, and that way that's the origin of how people figured out the universe is expanding, because they look at all the distant stars and the lines are slightly shifted, very slightly. How did these experiments become possible? Because people actually developed these spectrometers that could measure very sharp, wavelengths of light. So, and this was, as you know, since it gave birth to quantum mechanics, it's before quantum. So, when light was still understood as just Maxwell's equations and all that. Okay. And so what's going on here? I think you probably have seen this. From here, it was realized that these lines correspond to. So how is light interacting with the gas? It is interacting with the electrons in the gas. So the matter, which is say hydrogen atom, has proton or a nucleus, and it has electron, right? The protons are very heavy, right? You know that, about, let's say, roughly 2,000 times heavier than the electron. And then you have an electromagnetic wave come along that has an oscillating, electric field that looks something like that, right? So the electric field is going like that. So you can imagine it will start trying to jiggle these charges. It's a charge and it's electric field, so it's going to. But this one will jiggle much more than this one. It's heavier, right? This one is heavier. And so the interaction with the proton will give you some sort of a fine structure. We're going to neglect that right now. We're going to look at only the interaction with the electron. So it's essentially like as if this is frozen in space, whereas this is kind of responding a little bit to the electric field as it goes through, right? And the fact that these lines are discrete was what obviously puzzled a lot of people. Why are you seeing these discrete lines? And then Heisenberg really made the big breakthrough, saying that these are basically electrons are not classical particles, and they behave different equations of motion, right? And I'm not, this is not a course on quantum mechanics, but what I want to say is the philosophy, how did it come about, is that he said that the absolute energies are not relevant here. What we are observing here, these lines, each of these lines corresponds to a difference of two energies that are allowed for the hydrogen atom. So differences of two energies. No? And why is it so? Basically, it's saying that I have a certain energy. So hydrogen atom, you can picture now, it's a proton, which is a positive charge. And what is the Coulomb potential an electron will feel if you put it in a positive charge? The Coulomb potential is, minus E squared over 4 pi epsilon 0 times the distance from the electron charge. This is Coulomb's law, right? And therefore, if you plot the potential energy for the electron, it's going to, go something like that, right? Around the nucleus. And classically, the electron would basically just fall into this well, right? It would just and spiral in. And so Heisenberg had to say that because you are seeing such things, it cannot be true, right? That the electron will fall into the well. So he comes up with saying that the electrons, if they were classical particles, their energies would be kinetic energy over 2 times mass of the electron plus this potential energy, right? That would be classical mechanics. Kinetic plus potential energy is the total energy, right? Yeah, and Heisenberg said that this is not correct. You have to solve, because electrons are not classical particles, they have some wave-like nature, so you solve a new equation that I'm going to give you. And his equation, Heisenberg's equation, was very strange. It looked like this. It says, you solve this equation, and each of these quantities happens to be actually h and psi, h and psi. They happen to be matrices. So, and he says solve this equation, and a matrix like this will have, when you take when I say solve it, what you do is you do h minus E times an identity matrix. You find the eigenvalues of this matrix. You find the eigenvalues of this matrix, and he knew that matrices have discrete eigenvalues. And we take the differences of discrete eigenvalues, you get these lines. So that was the connection he made. And but obviously, as you see, nobody likes matrices because you're not trained in them. And then along comes Schrodinger, and he says exactly the same equation, but he gives the, writes the energy in a slightly different way, and it's not energy anymore. But he says, well, now you have operators, and 2m del x squared plus v of r. Let's write it in one dimension. So this times psi is E psi. So you solve this, or you solve this, you get those lines. And then that's the birth of quantum mechanics. He says, well, electrons being waves do not follow classical laws. They have to do this. And that's the reason why you're getting those discrete energies. I'm not going to go through all these details, but if you plug this in for the 3D problem, you will get, your En is minus 13.6 over n square electron volts. You'll get that, right? That's a very classic result, where n is an integer. It's a quantum number, 1, 2, 3, and so on. These are the energies allowed for the electron, for the hydrogen atom. Has nothing to do with the electromagnetic wave. It just happened that you have probed those energies with the electromagnetic wave. These are the energies allowed independent of the electromagnetic wave. So if you plot it now, 13.6 over n squared, n is equal to 1 will put you somewhere here. It's negative 13.6 eV. This is vacuum level. We're looking at energies. Let's say this is 0. This is 13.6. Right. Then you put n is equal to 2. You get that by 4, and you get a level here. Right. N is equal to 3, level there. And it gets denser and denser, and finally it merges with the continuum. And what's going on with the electromagnetic wave is, as the light comes along, it can only if the energy of light is matched with some of these differences. So for example, light can kick it if the electron was sitting in the ground state, in this state, and light comes along, and let's say the energy is a certain value, maybe like that, the electron can absorb it here. Get up there, right? If it absorbs it, that line is missing. I mean, that light is gone, right? But you might ask, well, if it absorbs, it's obviously going to re-emit it. And that's correct. It's going to re-emit it. But the re-emission, it may not go this way. It may go that way, and you observe it here. So that's the idea, right? So, and this is very interesting because it immediately tells you that, it gives birth to a whole new field in physics by probing matter in this way. And these are atoms. These are individual atoms. So what we are looking at this here, this is really not the absorption coefficient as much as it's basically what we are looking at there is kind of 1 minus that, right? Because the absorption coefficient is very high for those lines, right? Does that make sense? I mean, so the absorption spectra, the alpha for a hydrogen atom, therefore, will look how? If I were to plot it, how will it look? So again, I have hydrogen atoms in this gas, and then I have intensity of light here. I have light coming out, alpha d, and I'm going to plot now this alpha as a function of the energy of the photon. And instead of a semiconductor, now I'm plotting for the gas. So how will it look? So as you can see, for vast swaths of wavelengths, there's no absorption at all. And then there's a short peak, and then nothing, right? So something like that. And this is obviously idealized, but something like that. And these energies correspond to En minus Ens, right? Which is minus 13.6, 1 over n squared minus 1 over m squared. Then they have all these names, Leimer, Balmer, Paschen, and all that stuff, right? So that's the absorption spectra of atoms. And we are interested now at what happened here. I mean, the absorption spectra has obviously changed quite a bit as you go to the semiconductor or a crystal, right? And so we want to make the connection. Well, how is it that you go from this sort of thing to that sort of thing? And obviously that tells you a lot about the nature of chemical bonding and states and all that. And you can immediately see, we need to immediately ask the question that if I form a crystal, what are the energies allowed for the electron? Because for an atom, the moment you know the energy is allowed for the electron, you know how the absorption spectra looks. So the same question has to be asked now for the semiconductor. Or actually the right way to think about it is, here's the absorption spectra, now find out what is the energy spectrum of electrons in the semiconductor. Right? So any questions? I mean, this is again, I'm not getting into all the depths, just a motivation of what we are going to do. Yeah, please.
Like when in the spectrum, right?
Yes.
Why can you expect the emission to be in like all directions equally? Why do you just see it?
Very good question. No, that's a great question. So so you're asking, for example, here, why can't emission be in this direction as well? I mean, there is some amount of emission, but so that we will see. In fact, is determined by the what you call as the optical matrix element. Meaning, so what we'll have is electrons can occupy orbitals that are isotropic, like s orbitals, or p orbitals that are anisotropic, or d orbitals. And if it's anisotropic, and you have an overlap, meaning you transition from a s to a d, let's say, and the d orbital would look maybe I don't know, let's say there's a dx squared minus y squared that looks something like that, right? So when you take the transition of something, typically s to d is 0, but that gives it some direction now. If the orbitals are anisotropic, then the transition can proceed in certain directions preferentially over the others. Now you might think hydrogen atom is completely isotropic, right? But as a result, I mean, to a first order, if you track your spectrometer all around, it will be relatively isotropic. Therefore, the one way to think of it is the light that should have come out here has been divided by the whole spherical volume. Therefore, the intensity here has gone down quite a bit. Does that make sense? But in semiconductors, what we'll see is specifically is, for example, you're making LEDs or lasers. You want the light to come out in a certain direction. You don't want it to go in all directions. So you can actually design the semiconductor such that the light will come out from the edges or from the top. You can design it. And that is dependent on the matrix element. There, in a semiconductor, you can break the symmetry very easily. It's not completely isotropic. And that's an actually important point. As an example, okay, here's an example. You take the same gas, hydrogen gas, and instead of the hydrogen, just being like that, let's say I put 2 electrodes, okay, a capacitor, and then apply very large voltage. It's a very large electric field. I apply a very large electric field through the gas. So do you know what will happen to this spectra if you apply a very large field? So, yeah. Yeah, good point. So if a field is large enough, you are going to pull out the electron ionized. Let's say we don't ionize it. We are below that limit. We don't form the plasma yet or something like that. What happens to the energies? So classically, let's think of what will happen classically. And this is very important because so classically again, so the electron was going around like that, and you came in with a very large electric field. So the electric field is going to, positive charge is going to go that way, negative charge is going to go that way, right? So originally, before you apply electric field, this electron cloud was more or less symmetric around the nucleus. The moment you apply electric field, this doesn't move much in some sense, but the electron cloud gets deformed. Right? So what happens is you have positive charge, but now the electron cloud is electron is gone a little bit that way. So maybe it's kind of become a little more oval-like thing, and now you have a centroid of the negative charge, a centroid of the positive charge. They're not on top of each other. They formed a dipole. Each atom has formed a dipole. So and you can actually solve this in the presence of an electric field. So what happens is basically these lines shift. They shift. And some lines, so these will shift, and some lines can split. Because it'll break some of the symmetries. As you can see, the electron initially was completely spherically symmetric initially. I apply an electric field. Now the electron has a preferential direction, so you have broken a very large symmetry here. Right? And whenever you break any symmetries like this, the energy lines shift, some of them split, and all that sort of thing happens. Right? And in a certain sense, that's also what's going on here. That's also what's going on here. In a crystal, what you have done is you have put the atoms, so close to each other, and the electrons, and so now you have broken all sorts of symmetries now in certain directions and all that, right? And the electrons are not free to move in any free direction anymore. They only move along certain crystal orientations. These are called crystal field splittings and all kinds of other things. So that's what leads gradually from the atoms to a band structure like that. Similarly, you can put a magnetic field. So electric field will basically force the electron to kind of be confined in some sense in one direction along itself, right? Whereas a magnetic field will confine the electron to kind of, classically, if I apply a magnetic field in this direction, the electron always wants to do circles around the magnetic field. So it won't want to, so it breaks the symmetry in two directions and all kinds of things. And similarly, so if you apply a hydrogen atom, you apply magnetic field, it splits into, this Zeeman splitting, so it splits as well. Okay, so, and in a certain sense, what I'm trying to say is as you go from an atom to a crystal, you're really, the internal fields, internal crystal fields are evolve, make this, go from here to this sort of a detailed structure that we're looking at. Okay, any questions? All right, if not, so let's actually go over to this what we're going to do is look now at the absorption coefficient in some detail. But as I said, I want to look at this part first. It's called interband transition, where you go, the photon comes in and it kicks an electron from what we call as the filled valence band to the empty conduction band. And we're going to discuss this in detail today. Now, let me just say that the absorption coefficient here is large, and 10 to the power 5 or so inverse centimeter, and it is positive. What we will see maybe towards the middle of the semester is you can actually force a compound semiconductor to go into a situation. This is very interesting, and it's a good time to point it out. You can force a semiconductor to go into a situation where the absorption coefficient will become negative. It's very interesting. Negative absorption coefficient. So what does that mean? It means I have 5 photons coming in. I have maybe 10 photons going out. So I have more photons going out than what has come in, right? And so that is called population inversion, right? And you have optical gain. You have, you know, a certain number of photons coming in, more photons going out, and that's the heart of a laser, a semiconductor laser, where you have amplification. It's a stimulated emission because of amplification of light, and we're going to see that. And if we understand the absorption coefficient of equilibrium situation, a highly non-equilibrium situation leads to this inversion condition, where you inject a lot of electrons and holes, and you basically make the conduction band full, but the valence band mostly empty, and then you invert the population, and then this becomes negative, and you get optical gain, and that's the heart of laser, making a laser. So that's obviously lasers are one of the most useful applications of compound semiconductors, and it's an important property, and it's very deeply tied to the interband absorption coefficient. And then there's fun things like excitons and all these things we'll talk about also. Okay. So. Okay, so with that sort of a basic background, we can move on now and start looking at realistic semiconductors. I don't want to go by slides anymore, but okay. So yeah, you're going from atoms, discrete states, to a crystal now, and we have a faint idea it's going to form bands, but we're going to spend a little bit of time writing down a few very simple models to find out what are the bands of a semiconductor, So what we are going to do now is look at simple cases first, and we'll start with motivating the compound semiconductors. Okay. So for example, here you were transitioning maybe from a s to a d or a s to some other orbitals, right, for a hydrogen atom. Now when you put the atoms together in a semiconductor to form a semiconductor, then the electrons were still in some sort of atomic orbitals, s orbitals, p orbitals, d orbitals. And for silicon, there are s and p orbitals, and we're going to look at it in specific detail for most semiconductors. Gallium arsenide, which is a compound semiconductor, again s and p orbitals, gallium nitride, and so on. So we're going to start looking at them. Let's look at the orbital nature of some of these. And I hope you have taken enough atomic physics and such that, so if I ask you, well, tell me the orbital occupation of electrons for gallium, you should be able to write this down, which s orbitals, which p orbitals, and all that stuff. That should not be a problem. And s orbitals, as you know, as we had talked about, are symmetric, spherically isotropic, and p orbitals are linear along x, y, or z. And the d orbitals have, there are 5, and they have different shapes. D orbitals had not entered semiconductor electronics till there's moly sulfide and these things came along, and now these have d orbital conduction valence band states, so you have to consider them, and we will talk about them when the time comes. Okay, so carbon, s 1s and 2p2. So 4 is the number of electrons in the outermost shell, if you might. So as you know, so this is 1s, this is 2s, and 2p, right? So this is 2 is the outermost shell here. Silicon 3 is the outermost shell. Germanium, as you go down in the periodic table, you go to higher and higher number shells. So the electrons occupy them. And if you go down group 4, these are all the elemental semiconductors. And for them, obviously the outermost shell looks exactly the same. You have, for example, for silicon, you have 1s2, 2s2, 2p6 combined together. That is so that is basically you have a neon. I mean, this is the shell structure of neon, right? Which is a noble gas, or noble gas. What do you call it? Yeah, I mean, basically unreactive, right? And then you have the 3s, which is going to give it all its chemical properties. What do we mean by that? let's look at this picture again for a hydrogen atom. So what we are trying to say now is I'm trying to take the atom and put them together to form a crystal. So what's going on now is, let's look at silicon or any of these. So now you have obviously in the nucleus you have protons and neutrons. Neutrons are not charged, protons are, but you have a, maybe let's look at carbon for a simple example. You have 1s2, and then again they also will form, the nucleus will form even deeper well because it has much more much more number of protons than hydrogen atoms, even deeper. And then again it will form this ground state, excited, and so on. That's just a pure carbon atom. Now this energy here is 1s, right? And then similarly you kind of go up, so there's 2s and 2p and so on. Right? And what we have here is not just one carbon atom, but there's another one very close to it. Another one very close here, right? And another one, and now we have a crystal. It could be graphene, it could be diamond, one of these two crystals. So again, you have this here, that there, and that there. And I think, again, this is not very important right now, but what we are trying to say now is these deep core states, they still are like atomic states. They have not been perturbed much because of bonding, chemical bonding. The ones that have been perturbed are the ones in the outermost shell, 2s2 and 2p2, for example, 2s and 2p, because their wave functions kind of stretch out a little bit and they overlap between the two, whereas this is kind of really not overlapping much. This is all approximations. You can calculate it more and more accurately. But that's kind of a very simple picture. And because of this overlap, that's the idea we're going to develop now. Because of any overlap, you're going to form a band now. The states that overlap are going to form bands. The states that don't overlap are going to still look like atomic states. So there's this dichotomy between the two. And the atomic states are very deep. So if you want to probe them, you can actually increase the energy of the photon, not stop at 10, but keep going, kilo electron volts and all that, and then you will see them. Those electrons will come out then. But if you're looking at low energy spectrum, you're not going to see them because there's a huge gap to excite them. Okay, so does that make sense? I mean, we are looking at the merger of these bands, and these will combine together now to form bands. And the goal for me for the rest of the class today is to write down an expression for that band. We want to write down an expression for the band structure quantitatively. The simplest model. And you can go into it as much into depth as possible. There's DFT codes. There's all this stuff today. But we are going to just develop like a very simple tight binding model. You draw the band structure, because once you write down an expression of the band structure, you can calculate a lot of other things from there and understand the spectra and all that. Okay. So, and as you can see, as you go deeper into in the periodic table, you have a lot more shells that are occupied, and the outer shells get farther and farther from the nucleus, and so the chemical bonding gets weaker and weaker. Does it make sense? And therefore, if you take tin and you heat it, it will melt at a very low temperature compared to a diamond, for example. So the melting temperature goes down. I mean, all these things, because the electrons are very far, they're not strongly connected to each other. I mean, there are all these properties we'll come to later. Right now, we are interested in the electronic properties, so let's look at that. Oh, yeah, the other thing I want to say is, obviously, group 3 has 3 outermost shell electrons. Group 5 is this. It has 5 outermost. Group 4 has 4, and so on. So you can form, when we look at the bonds, you can form chemical bonds. If you're forming a 3D crystal, then if you want to form a 3,5 or a compound semiconductor 3 crystal, what we'll see, there's a rule of 4, meaning if you look at your basis atom, the minimal unit, you add up all the outermost shell electrons and divide by the number of atoms, it should be 4. That's the rule of 4 for compound semiconductors. So you can do 3,5, you can do 2,6, you can have some more complicated structures and such things. There's a little rule which is formalized, and I'll talk about that part later. Okay, So let's look at a very simple band structure today, and this may be too simple for people who have looked at it, but I think it's very important because not only does it illustrate what is a band structure, it also illustrates the fundamental, very big fundamental difference between an elemental semiconductor and a compound semiconductor, like between, say, something from group 4 and 3,5, or graphene and boron nitride. It's a very important difference between the two. And we are going to look at this. So we're looking at a band structure. So if you have taken a course on solid state, you have seen this many times over probably. But regardless, I think it does illustrate quite a number of important points about the band structure. So we're going to just do that right now. Okay, so this part is let's just call it band structure because I'm not a big fan of names. So what is band structure? So essentially what we're going to find is what is the energy versus the momentum of electrons that are allowed in a crystal. Right? So in the atom, there is no momentum because the electron is tied, it's localized to the hydrogen atom. It cannot get away. So it cannot have momentum in any direction. So there is no EK. What you can think of is the energy of the electron for a hydrogen atom is discrete, and basically, there's no K concept of K because it's localized. But in a semiconductor, we just saw that you have localized states and you have states that can move, that form bands and they can move. For them, what is the E versus K? That's really what we're asking right now. Well, okay, so we're going to look at it. So generally, I think you kind of have seen this. It looks something like that, and maybe more bands and all that stuff. So we're going to look at that now. But we're going to start, because we're doing tight binding model, from the atomic states. And the example we're going to choose now is graphene or boron nitride, either way. What you are going to do as a part of your first assignment is maybe gallium arsenide and silicon. So I'm going to do 2D now, you're going to do 3D, and the method is exactly the same. There's really no difference. And I think this is an easier thing to do in the class, and at least one good thing that has come out of 2D crystals is we can cover the band structure in one class. So that's nice. So we're going to just do it for graphene. Oh, sorry, boron nitride or graphene. This is a 2D crystal. So I think you know this. So essentially, you have carbon atoms in a hexagonal lattice. Or if you look at a boron nitride, you have boron and nitrogen, boron and nitrogen. So essentially, instead of two carbons, you have boron and nitrogen. So we just saw that the orbital structure of these are S. So carbon is 2s2 2p2, right? And look at boron is 2s2 2p1, nitrogen 2s2. So when you kind of combine two of them, one boron and one nitrogen, it looks the same as two carbons. Does it make sense? So both carbon and boron nitride can crystallize in 2D crystal form or 3D crystal form, both of them. The 3D crystal form of carbon is called what? Sorry? Yeah. Diamond, right? I mean, that's the so 3D crystal form is diamond, and 2D crystal form is graphene. Similarly, boron nitride has a cubic version of it. It's called cubic boron nitride. Extremely difficult to fabricate. People are trying, very hard to fabricate. Cubic boron nitride, and then the layered form is called hexagonal boron nitride. So atomic thin layer. So what we're going to do is look at how do we calculate the electronic band structure, and typically. There are courses where you, for the whole semester, you calculate band structure. So as you can imagine, we're going to cover it capture the essence of it, but not get into too much details of numeric details and all that. So we are going to look at carbon atoms in a hexagonal lattice, or boron nitride for that matter. So and what I'm trying to actually, let me plot it in a slightly different way, in a 3D form. I don't know how accurate it will look. So, okay, I'm just going to pull out a small part of the whole crystal, so it looks something like that, right? something like that. It's a atomically thin membrane, and carbon atom or boron atom, let's say, or nitrogen atom. As you can see, you have 2 electrons in the s orbital and 2 in the p orbital, right? So there is a s orbital. I'm going to just sketch them. Okay, so there is a s orbital. Then there are 2 electrons in the p orbital, right? And these 2 can. So the px. Remember, the p orbitals can be px, py, pz. Right? So there are 3 directions. And what's going on here? Let me just draw a sketch first, and then I'll explain what's going on. So the s orbital is obviously centered at that orbit around the nucleus. Now, and it gets a little stretched out and all that, but that's I'm not getting into too much detail of that. But you see, carbon is bonded to 3 other carbon atoms here. 3 other carbon atoms, not 4, but 3. What I said to you earlier about the rule of 4 is true for 3D semiconductors. Okay? Here it looks interesting. So you have p orbital that way and another p orbital that looks like that. So there are 3 p's that have actually hybridized with the s and form this sort of a elongated on one side, short on the other. Elongated on one side, and those are the bonds, 3 covalent bonds. So if you look at it, this carbon atom also has formed, this sort of a this one has formed this sort of a orbital, and that's the chemical bond. The overlap of the 2 electron orbitals is the chemical bond. Okay, so what we are going to do now is count which orbitals are involved in this sort of a behavior, and say which, because you see, if you go to down in the periodic table, there are lots of orbitals that are present, but only some of them are chemically involved, right? So we want to first select those. And what we'll see for graphene and boron nitride is even these orbitals are actually not going to be important for its electrical and photonic properties. Even these orbitals, the one that's form chemical bonds, somewhat different from traditional 3D semiconductors. So ideally, how would you calculate the band structure of this? That's what we want to ask. I mean, how do you go from here to there? That's really what we're asking. How do you calculate EK from the crystal and the orbital picture? So the way to do that is, basically the brute force way of doing it is the following. You say, well, I have, I realize that in the graphene crystal or in the boron nitride crystal, you have the minimal repeating unit of the crystal is actually not 1 atom but 2. 2 atoms is the minimal repeating unit, and that's called the Bravai lattice, and that sort of thing. Meaning, so if you take these 2, these 2 atoms, and you basically translate it by this vector or that vector, you can create the whole crystal now. If you choose only one, you can't do it. You can try, you can't do it. So this is the minimal, and it's called the basis, right, or the primitive cell or the basis. And this shaded parallelogram would be kind of called the primitive cell of the material. Meaning, by repeating this parallelogram, you can fill this whole space and so on. So what we need to consider then is this 2 atoms as 1 unit, and we want to write what are the energies allowed for those 2 electrons, for the electrons connected to those 2 atoms. That's really what we want to write down. Now, the moment you go to 2 instead of just 1, see, your Schrödinger equation or quantum mechanics tells you that you solve Heisenberg's matrix equation is E psi, and you will get your energy eigenvalues for electron, for hydrogen atoms. The moment you go to 2, it's a molecule. So electron could be here or there, right? It could be there, here or there. And so for the procedure for that is you do a linear combination of the 2. Right? Meaning, if you have a site A for electrons and a site B, could be sodium chloride or hydrogen chloride, anything like that. Right? The 2, right? So if the electron is sitting here, independent of this, it has a certain energy. Let's call it EA. If it's sitting there, independent of that, it has some other energy. It's EB, right? And this is basically why Heisenberg introduced matrix mechanics. He says, well, if the electron was sitting, completely in A side, then I will have a state that will look like 1, 0, and it will have energy EA. Let's say there was only A, it will look something like that. That's the idea of matrix mechanics, right? But if it's B, there's another atom. It has a different energy. I'm not going to worry about what these are. These are some some vector with some coefficients here, and now I don't know what this energy is, right? I want to find it now, and the procedure to find it is solve this equation. It's a matrix equation. Solve it. Now, if, as you can see, because of the electron overlap between, wave functions kind of overlap a little bit between the two, there is some sort of an overlap term for the electron. What is the energy that the electron could typically lower? Whenever you allow electrons to spread out in space, they're going to lower their energy. It's delocalization, lower its energy. If you let it spread, if you confine it, it's going to raise its energy. Right? So this term is typically going to be negative. It's called a hopping term. And this will be a Hermitian matrix, so this complex conjugate will be here. This is the most general form. And every band structure like this is basically that. It's written in 8 by 8 or 16 by 16, 30 by 30, whatever that is. Depending upon your unit cell, the size of it can increase. But that's what it is in the end. I mean, there's no more complication than this. If you understand this, you can actually calculate all the band structures. Okay. Any questions? I mean, I know I'm going through it fast, but this is a general method to do it. And now the way you would do it is, if it was a course more on solid state or other things, we would also look at the eigenfunctions. These would be called the eigenfunctions, and all allowed values of E would be called the eigenvalues. And this is a plot of the eigenvalues for different Ks. This is allowed value for K is equal to 0, allowed eigenvalue E. So what we will see now is for a crystal, this will become a function of K, and then you plot it then. So that's what. Okay, so but for a molecule, this is actually pretty trivial, because 2 by 2 matrix, you know how to diagonalize, and how do you solve it? You say, well, I'm going to take this whole thing to the left and write it as EA minus lambda times my unknown energy, EB minus lambda times, sorry, what am I doing here? Minus my unknown energy. Let's just call it U and U star, the off-diagonal terms. Okay? Do you see what I'm doing? The same thing is equal to 0. Okay? So it's an eigenvalue problem. Find its determinant and solve for E. Okay? And this is a trivial one because you get EA minus EB minus E is equal to U squared. Right? That times that minus this is equal to 0. That's the equation. Right? So from here, it's a quadratic equation, right? And I think what you will get from all these manipulations is that the energies will be EA plus EB over 2. And this is probably the most important result for band structure of semiconductors, if not, so yeah. Right? So you basically get it's a quadratic, so you solve it and you get that. And in a molecule, these energies, you have a plus and a minus. There are two roots, right? You started with 2 electrons with 2 energies, and when you end, you will still have 2 energies. It's just that the energy might have shifted from its original values. What do I mean by that? The energies, when the electron was sitting here or there, was, let's say, EA and EB, right? They were like that, but because of the interaction now, you have, this and this. So typically it would do something like that. Shift, right? And so it shifts around the midpoint, EA by E plus EB by 2, around the midpoint, right? And the splittings, this and this, are plus minus this, right? So the difference of this is, as you can see, that, right? Right? And I think you can see very clearly that if I turn off my interaction or hopping term I will recover these again. Right? I'll get En if you turn it off completely, right? The hopping term, right? Is that clear? Okay, yeah. So now what we are going to do is, instead of 2 atoms, we are going to have an infinite number, but this structure is what is going to repeat. From here, there. Basically, I'll take this molecule in some sense and translate it there, there, and then you can make the whole graphene crystal now. That's the idea now. Still, in this picture, when there are 2 atoms, there is no K. Electrons are still localized to the molecule. They're not going anywhere. I mean, they're tied to the 2. But what they have formed is what you call, this is called the anti-bonding orbital, and this is called the bonding orbital. Meaning, if you look at the wave functions of the 2 electrons, the higher energy state will have a node. Meaning, well, so the wave function for the wave function will look like that for the electron for the lower state, and for the higher state it will look something like that. There's a node in between. If you take mod psi squared, the electron mostly spends time in between the 2 for the lower energy state, but it spends time away from the middle for the high energy state. That's the anti-bonding state. Okay, so now we take it to the band structure from here. Essentially, we're going to repeat it. And this is where there's a slight change we have to introduce. And let me just maybe put it here, and then we plot the results. So now what I have is this unit is going to repeat. Yeah, right? And what is it going to repeat by? It's basically going to go, for example, this is the unit, and it's going to go, a lattice vector this way, a lattice vector that way, and a lattice vector that way. There are like 3 units for the graphene crystal in particular. If you look at gallium arsenide silicon, there'll be 4. So there'll be basically, yeah. So it's a 3D crystal. You need one more in some sort of direction. But so the way to deal with that is, again, you have a certain wave function or a eigenfunction here. And this is called, again, you can go through this in detail if you haven't, but the total wave function will be written in this form now. This is the phi is this. It's the function that corresponds to 1 unit, 1 molecule. Or it's called the orbital at some location, Ri. That's the orbital. At this point, you shift Ri to that point. This is a it's a lattice vector. You shift it there, you change this. Shift it there, you change that. But the shape of it is the same. You just rigidly shift it there, rigidly shift it there. That's and the wave function. And the total wave function in a crystal, as you go from a molecule to a crystal, becomes this. And this is called Bloch theorem. I'm not going to try to derive it, but the total wave function will look like that. 1 over some normalization volume or number of cells. You take this wave function, multiply by phase factor. That's important. And what is that phase factor? That's really the critical part, because even if you don't really understand the whole Bloch function picture, it's not a problem, because in the end we are going to say what is this matrix, and the matrix will be trivial. You can write it down looking at the structure directly, so in the tight binding picture. But this is kind of the important factor. Here is the K that appears, which is your EK diagram K. This is the K for EK. Everything else here, this is a lattice constant, you know it. I mean, if you know the crystal and the crystal structure, you know Ri. What are the lattice constants and all that. And this part, what is nice is you don't have to know it to find the band structure. If you need to know some other things like optical matrix elements and all, you need to find the phi. But if you want only the band structure, as you can see, I got my band structure without knowing what is my eigenfunctions. But if you are running MATLAB Mathematica, you will also get it for free, because it's a matrix equation. You can ask it. But to find the EK diagram, you don't need it. And that's the interesting part. So what I'm saying is, once you take this and you plug into your Schrodinger equation and do a little bit of this hopping term, that's I'm going to write down the final result that you're going to get. And again, the Hamiltonian looks exactly similar. There's really no difference, almost no difference. Except, as you can see, the hopping terms are not just to one other atom, but it will be to more now. Right? There'll be, for example, for graphene, there are, it can go, I think it's not been discussed, so it can go that way, or it can, basically it has two repeating units, A1 and A2. In fact, this third direction is basically a vector sum of these two. It's a linearly, So the way to look at it now is you have two lattice vectors, A1 and A2, and the third actually is basically 0, 0. It's this point, that point, and that point. These are the 3 points. So you have A1 written here in terms of some lattice constant in 1 angstrom or something like that, 1.5 angstrom, A2. Okay. And the Hamiltonian looks exactly like that. Let's say we are talking about boron nitride instead of graphene, or whichever be it. So what I'm trying to say is, here is the energy still. This energy is still the energy of the electron to sit on one atom. This one is the energy for sitting on the other atom, independently. Yeah? And the off-diagonal terms is the hopping term, and that's the important one here. And now that has K. K is the EK diagram K. It has this K. And it comes about because basically you take this and you overlap it, and you get, Ri minus Rj, and that is really your lattice vector from one point to the other. So you project it on other things. So that's the detail. All said and done, what's going to happen here is I have my Hamiltonian now, or the problem that I have to solve to find the eigenvalues is energy of site A, energy of site B. And then there's a hopping term, meaning if the electron was here, what is the energy lowering if it goes there? Right? That's the hopping term, which was our off-diagonal U term here. Here it can go to 3 sites, and let me write it down. It's going to look like this. T is the hopping term, energy in 1 electron volt, 2 electron volt, depends on how strong is the chemical bond and all that. And then you have a sum of phase factors. You have like, e to the power I, k dot, R1 plus I, k dot R2 plus e to the power I, k dot R3. If there are, there are 3 vectors, but here R1 happens to be 0. It's just that. All right? So that's just 1 plus R2 is actually what I'm calling A1 here is R2 for you. So you plug that in, A1, plug in A2, and that's your hopping term now. Right? And similarly, this term is just the complex conjugate of that, so you do 1 plus e to the power minus I, k dot A1 plus, the complex conjugate is just going to take e to the power I will turn into e to the power minus I, k dot A2. Okay, so here's your new matrix. And you are guaranteed that the eigenvalues are real because it's a Hermitian matrix, because this is. Okay? So find the eigenvalues now. Find the eigenvalues and you plot, you're going to get your band structure. That's how you get the band structure. Right? So let's look at this example. So this is the reason I chose this 2D crystal is because you can exactly solve it analytically, and you get an expression and you plot it. Yeah? What's the expression? Here's the expression. It looks a little complicated, but the way it's written is EB and EN is the energy. Let's say it's boron nitride. The energy for it to sit on boron, the energy for it to sit on nitrogen. And then T is the hopping energy, which is here, and A1 and A2 are given. So you just plug them in, and here's the band structure. Here's the expression for the band structure. A is again the sum, EA plus EB by 2. Right? And this B that sits here is still the difference, EB minus EN by 2. The difference. And here's the expression. Make a plot of it, and that's the band structure for you now. Here's a plot, EK diagram. Remember now K, very important point. The K here, the momentum, it's a 2D crystal. So the electron can move in 2 dimensions, right? So the K has Kx and Ky, or K and theta. So it has a 2-dimensional crystal. So the K is 2-dimensional, and therefore you get Kx and Ky's here. So you make a plot of it as a function of Kx and Ky. And here's the plot. And you put in some numbers here, EB, boron, and nitrogen. These are typically experimentally measured values, and I think I have it written somewhere. Yeah, I have some stuff. So it's like 2.9 EV minus 2.9 EV. Hopping term is something like that. Lattice constant. That's all you need to know. Hopping terms, on-site energies, and lattice constants. Done. With that, you get the full band structure. So you plot it. Here's how it looks. You can kind of take contour plots of, say, the conduction band, and you realize that it has 6 minimas and all that sort of thing in this little window we are plotting. They are typically called the K and K prime points and all that sort of thing. Okay. So what I wanted to really talk about now is that clear? I mean, so the procedure. Right? The procedure is, it comes from this block theorem, you plug it in, and the major change to the molecule picture is just this, that you have these phases, right? And the electron can basically move between, the electron, since it is mobile, you have to actually calculate the eigenvalues as a function of k, as a function of k. Does that make sense? Yeah. Essentially, it's just that, these values, but now as the k is tuned, as the electron moves, its energy can change. It gets more kinetic energy. So this is the potential minima, and then the rest of it is basically kinetic energy, h squared, k squared by 2m. That's it. And already right away from here you can see there is a clear band gap, and the band gap, just like you have the bonding anti-bonding picture, no? Right? This. So band gap is basically like, you know, related to this sort of a term here, and here it happens to be 2 times b, or EB minus EN. That happens to be the band gap here. Band gap is like 2 times b, and this is done for boron nitride. It's about 5.8 electron volts. But now, after you calculate the band gap, what you can go is go very close to the minima of these values, you know, minimas, and then expand the energies around there. And that's what's called the effective mass. If you write it, you know, this parabolic expansion near the minima is called the effective mass. And in this analytical model is beautiful. You can get the mass directly as a function of the band gap and all that. Because there are really 3 parameters here. There's a lattice constant, there's a hopping term, and basically the on-site difference energy. All that. So you get effective mass. And for boron nitride in this simple model, you get about 0.6 times the free electron mass. That's the effective mass. Rough. Okay, so you can actually fix your 0 at some point. I'm not getting into that detail right now. I'll go to it when I talk about graphene, the very next stage. So any questions? I mean, this should be simple enough. Hopefully you can, you know, apply it and just run some codes, and then actually you can calculate it by hand and calculate it. You don't need any computer programming for this. And it already gives you all the ideas of what is a band structure, what are the allowed energies for the electron in the crystal. That's a couple of other things. One of them is, if you plot the structure, you see there will be actually 6 points at which the band goes through a minimum, and at the same point the band goes through a maximum at the same time. So these are called direct band gap semiconductors, where the maxima of the band, this is the valence band, which will be full. This is the conduction band. If they are at the same point in k space, that's a direct band gap. If they are at different points in k space, they may be at different points. That would be an indirect band gap. There are 6 points, but if you look at a hexagon, you realize immediately that, you know, this point is shared between, you know, 3 nearest hexagons, right? So you should kind of do 1 by 3 times 6. That's how many minima there are in every unit cell. And that every minima is called a valley for obvious reasons. You can see the picture, it's a valley. So it's called a valley degeneracy. How many valleys are there in the band structure? For graphene, for boron nitride, it's 2. The 2 valleys. In what you call the first Brillouin zone, this hexagon actually would be called the first Brillouin zone. So even though there looks like 6 because they are shared, it's actually 2. 2 valleys. So valley degeneracy is 2. And then there's the spin, which I don't want to right now get into right now. So there's also spin degeneracy. Okay. So now what's going on in pictures? It's almost out of time. So what's going on in pictures now? So when light comes in, this valence band is full of electrons in boron nitride. This is empty, so it kicks an electron out. As long as the photon energy is larger than the band gap, which is 5.8 electron volts, it is going to get absorbed, right? And that is really the step that you will see. So when the photon comes in, and this is 5.8 eV, when you plot your absorption coefficient as a function of h bar omega, there will be pretty much nothing, and then, you know, the moment you hit the band gap, you know, the energy, there will be a step here.
What does it begin to decrease?
Good point, and we'll discuss that. So we'll calculate the absorption coefficient. What we'll see is basically it goes as h bar omega minus Eg, but there will be in the denominator there will also be h bar omega when we calculate the full-blown version of it. Of the absorption coefficient. There will be the total absorption coefficient will be, there's some other coefficient, but there's a energy dependence in the denominator too, which is why it starts. As your energy goes up, it starts decreasing. Okay. That's a little detail we'll come to when we talk about photonic properties in more detail. Okay, so now what you can do is, in the same shot you have solved many problems for 2D crystals. You can now also do, well, what is it for graphene? For graphene, your on-site energies EB and EN are actually the same. It's both are carbon atoms. Right? They're both the same. Therefore, the difference is 0. Right? This B is 0. Therefore, the band gap is 0. You can get it right away. And you plot the same picture again, and here's graphene band structure. So you have cones now. You have the Dirac cones for graphene. Because the two on-site energies are the same, the gap is 0. This would be an elemental semiconductor. Boron nitride is a compound semiconductor. So you have a broken symmetry of the electron state, which is why you go from 0 to 5.8 eV band gap. It's a very big change. And then for graphene, you basically, it's the same band structure. Really, you're just playing with different coefficients. That's all. So A, B's are different. That's all there is. There's no difference. And similarly, it has two valleys and all that. And if you look around the minima, it's very. So one of the things I kind of not glossed over, I was trying to, I think I forgot to say, is, each of these atoms is coming in with one S, and basically they are hybridizing, so you can have S, Px, Py, and Pz. Their valences are still 4, so there are 4 electrons, one in each orbitals, right, in some sense. But in graphene and boron nitride, you have sp2 hybridization for the chemical bonds. So these 3 bonds are what you call sp2. The hybridization is sp2, and there's one of these that is left out. And what we did here, all this stuff we did, is for that left out electron. These are the orbitals. These orbitals that would sit here are the pz orbital, the electron that's sticking out of the plane. It's not in the plane, but sticking out. The ones in the plane, which are the sp2 orbitals, these, if you ask me what are the energies of these orbitals, those energies are actually very far away from the region of interest. They are core, the core levels, they don't move, or they are very high energy, they never excite there. So these are the sigma, which are the sp2 orbitals. What we looked at are the pz orbitals, which are called the pi bands, pi orbitals. And all the action in these materials happen in the pi orbitals. Okay, so we'll just stop here, and I'll continue this in the next class. I mean, I don't want to go into too much detail. I'll give you a tight binding model for the 3D crystal, and you can apply it and look at it and start connecting it to the properties we're looking at now. All right, thanks.